Well, hello, everyone. Thank you for joining us for today's webinar, Cost-Benefit Analysis and an Argument in Favor of Replacing Mechanical Turbine Control Wind Sensors. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console, you'll see several application widgets for your use. For instance, when a question on the topic arises during the webcast, click on the Q&A widget and type in your question there. I'd encourage you to ask questions. And don't wait to the end of the presentation either. Submit your questions as they occur to you. And we'll try to answer as many of them before our time is up. So should a question deserve a full answer or we run out of time, it will be answered by email. We capture all the questions. A copy of today's single deck webinar and additional materials are available in the resource list widget. That looks like a green folder at the bottom of the screen. You expand your slide area by clicking on the maximize icon at the top right slide area or by dragging the bottom right corner. If you have technical difficulty, please click on the help widget, the one with the question mark. And an on-demand version of the webcast should be available tomorrow and can be accessed using the same audience link that was sent to you earlier. Today's webcast is presented using a slide deck and not a screen share or a live demo. If you want a copy of today's presentation, click on the green resource list widget at the bottom of your audience console and download from the documents listed there. Now, if you don't see the slide movement on your console, hit the refresh icon in your browser URL bar or hit F5. Now let me tell you a little bit about our speaker. And in fact, we have a sort of a guest question answerer today as well. Our guest speaker is Abraham Aguilar. Mr. Aguilar is the Director of Business Development at Lufft USA. He has a background in industrial automation dating back 8 years. His technical experience, coupled with his role as Weather Sales Director for Lufft, a manufacturer of weather sensors, has made him an expert in turbine control anemometry. His role at Lufft is to continue the company's market focus in developing its market research in the Canadian, USA, and Latin American markets. Abraham's responsibilities include business growth, partner acquisition, project management, technical support, and marketing. And then during the question and answer period, Abraham will be joined by Tristan Lee, who has worked on swapping mechanical wind instruments with ultrasonic versions. And Mr. Lee is employed in the United States Strategic Business Unit of the AES Corporation. He's a veteran performance engineer with an extensive background spanning nearly a decade in modern wind turbine design, operation, and project development of Ventus, GE, Siemens, and Mitsubishi turbines. It's quite a lot. He's been heavily involved and led various studies revolving around wind turbine meteorological systems, having published several white papers on his findings, along with patent-pending algorithms related to the wind distortion induced in a post-rotor wind measurement system. And let's see, and that's enough for me. How about if we get rolling? Okay, Abraham, I think the microphone is yours.
Well, Paul, thank you very much for the opportunity, and thank you everyone for joining us today. Special thanks to Tristan Lee in joining us in our Q&A session as well. Before we start, I wanted to kind of give everyone an introduction as to who Lufft is and where we come from. Lufft was actually started by Gottlieb Lufft, founded the company back in 1881 in Stuttgart, Germany. In 1989, a group of investors kind of took over the company and redesigned the company to become more of a digital-focused company. The gentleman in the middle of the picture is Klaus Herzl. He is the CEO and Managing Director of Lufft, currently managing our entire business unit for the company. And the gentleman to the left of him is Axel Schmidt-Hoops, which is our senior engineer and the main designer of a lot of the products that we currently sell at Lufft. Presently, I wanted to let you know a little bit more as to where we've come from in the last 130 years of doing business. We are now part of the Danaher Group, which is a $20 billion organization, and we're ranging everything in the globe when it comes to weather information systems as well as industrial components. Far as where we are in regards to the world, Fellbach is the headquarters for Lufft. We are based close to Frankfurt, in the middle between Frankfurt and Munich, and we also have subsidiaries in the United States as well as in China. I myself am based out of the LA branch, or the Santa Barbara office, which is in the southern coast of California. In 1903, Lufft became a market leader, or Lufft became a market leader in the metal barometer business sector. And presently, we are now involved in a wide array of industries and markets, ranging from industrial devices for laboratories, as well as cabinet control sensors or transportation sensors for data logging capabilities. We also have a market segment in traffic, where we're focusing on RWIS, which is Road Weather Information Systems, with a lot of the Department of Transportation divisions within the United States and the Americas. We also have a mobile weather sensor that's able to capture real-time weather on a consistent basis and provide that information to the cloud for real-time monitoring. But for today, we want to focus on the business sector that we cover in regards to wind and weather. Primarily, our biggest focus has been in the renewable energy, including solar and wind, which I also cover meteorological, hydrological, and building automation opportunities. For the last couple of years, I've been able to go to different types of conferences and workshops where I meet with and interact with a lot of operation maintenance companies. Pretty much the feedback in the industry has been that they're looking for a way to reduce cost and increase production overall. They've informed me that there's a lot of icing issues that cause production loss with the current sensors that are mounted on their turbines. And they want a simple to use and simple to implement solution that would solve a lot of the problems that they're currently seeing. They did inform me as well that they're having a lot of mechanical sensor issues where they require replacements, or that the sensors need yearly recalibration because of their mechanical components that are caused by wear and tear, so they need recalibration every year. They also informed me that they need a low-cost, robust sensor because this is definitely going to impact their bottom line. And of course, the sensor needs to meet regulatory requirements to be able to be installed. The sensor that we provide at Lufft is the Ventus. It's primarily designed for wind turbine applications. It comes with a factory certificate. Every sensor that we manufacture comes with a factory certificate. And so there really is no need for recalibration because there's no moving parts within the sensor. It's an ultrasonic sensor, so there is no mechanical components to it. The sensor has dual heaters that prevent icing from forming and also prevents riming. The dual heaters, there's a heater on the top of the sensor, the plate there, and then there's embedded sensors or embedded heaters embedded within the ultrasonic sensors to prevent any ice from accumulating. The sensor by itself has both digital and analog outputs, so that helps with the simple integration of any wind turbine currently in operation. And did our research, and we actually meet or exceed the NRC regulatory guide of 1.3 requirements, which is wind direction of plus or minus 2 degrees and wind speed of plus or minus 0.45 miles per hour. This sensor has gone through HOLT testing, meaning that our MTBF at 20 degrees Celsius is 22 years. So we have an MTBF of 22 years or so. The corrosion test that we've provided has passed, and we also have done a vibration testing on this sensor. There's also been an ice free testing. As you can see here in the picture, is a picture of the ice free testing that we did, where ice accumulated around the sensor, but no ice or ice particulate actually accumulated within the sensor head. And this sensor is an IP66 sensor. For this analysis, we're going to go over 3 different types of sensors. We're going to talk about ultrasonic Ventus, which, like I mentioned before, has no moving parts, includes a temperature control for icing events, has a lifespan. For this analysis, we did a lifespan of 5 years, which I mentioned we have an MTBF of 22 years. We understand there is a higher upfront cost compared to the other items or other sensors that we're going to be covering, but we are also understanding that within the higher cost, we'll be able to explain why the higher cost would be beneficial in the long term or the lifespan of a wind turbine. The sensor does provide wind speed and wind direction, but it also provides for other controls like being able to measure the signal quality of the wind speed and wind direction. There's a channel within the sensor, you could read that, as well as has a virtual temperature sensor where looking at the wind speed or at the particular of the air goes through the sensor, you're able to kind of capture a virtual temperature, and that's a channel within the sensor as well. Like I mentioned before, this has a digital as well as an analog output protocol directly from the sensor. Now, the cup anemometer, this is an example of a cup anemometer that's out currently in the market space. This could be or may not be exactly the same thing that you might have in your current wind turbines, but it's something similar to what's out in the market space. As you can see, it has a lot of mechanical parts which are subject to weathering. Of course, the weight and the inertia of the moving cups may negatively impact the accuracy of the reading. We understand that the systems like these have a low power requirement and they're inexpensive, at least in the upfront cost. There is a mechanical failure rate as high as 1 per year, and that's something that we calculated within the analysis as part of the assumptions, and may have a frequency to be recalibrated on a yearly basis. Similar to the cup in anemometer, the Vane anemometer has the same type of mechanical failure points, and there's also a portion where some of these Vane anemometers require a signal conditioning as well as additional wiring, which we've captured within this analysis. Other assumptions that we did for this analysis that we conducted interviews, and within those interviews, we were informed that about 40% of all mechanical sensors needed annual replacements due to failure. We did our research and we found out that on average, wind turbine technicians make about $23.46 per hour. This is added into our labor cost. There was a 5-year maintenance time to repair, or I'm sorry, 5-hour maintenance time to repair or replace the mechanical sensor. This 5 hours is for the labor cost of getting a technician out to the site and repair or replace the mechanical sensor. Like I mentioned before, signal conditioning as well as additional wiring are additional costs for mechanical units in some situations. And industry reports that icing occurs about 5 times per year. So we assume that if a farm has 100 turbines, then the probability of icing occurring is about 5%. And the information gathered informed us that about $40 an hour is lost due to in production when a mechanical sensor is down. We also assumed that it would take about 2 weeks for the sensor to be repaired on the field. So we took that into the analysis. When we calculate the numbers, we did a cumulative cost of the total cost of owning a mechanical sensor versus owning an ultrasonic sensor. And as you can see here, the total cost of owning a mechanical sensor that is non-heated is $1,819 compared to the Ventus, which is $2,112. If you look at the graph, we actually show that we could have a return on investment within the first year. Now, if you look at the total overall cost within 5 years, again, the assumption is that both sensors are being compared in a 5-year timeline. The cumulative cost of you owning a mechanical non-heated anemometer is about $4,730. And this cost is with the assumption that it's going to be a 40% replacement need due to a failure that occurs within the mechanical anemometer. This is how we calculated the $1,819 for the mechanical sensor. We took the base price of the mechanical sensor, added the shipping cost of $50. The labor cost, like I mentioned before, is $23.46 per technician per hour at 5 hours. The cost of failure is $40, which is the cost of per hour of lost production, times 5 hours to repair, times 40% annual replacement due to failure. For this particular situation, we added in the signal conditioning requirements that would be needed for a mechanical sensor and the additional wiring costs that are required for the mechanical sensors to operate. And we also incorporated the cost due to icing, which is 40% of production lost times 24 hours times 14 days until replacement is placed, and the probability of icing of 5% that accumulated to $1,819. Now, someone might say, well, in my case, I don't have any signal conditioning or any additional wiring costs, so what would the cost look like? Well, in that case, if we take away the signal conditioning wiring cost, the total cost of owning a mechanical sensor is $1,219. As I mentioned here as you see here illustrated. What does this do to our graph? It actually shows that return on investment, if no signal conditioning or wiring costs are included, the return on investment for owning a mechanical sensor compared to a ultrasonic is a 3-year return on investment, as you can see clearly on the graph. Now, how do we calculate the cost of the Ventus ultrasonic anemometer? The cost of $2,112 was looking at the base price of $1,945 for the base price of the Ventus. There's a shipping cost of $50 that we assumed, $23.46 for the technician times 5 hours to go up and replace the sensor. Now, because the ultrasonic we are not expecting to see any failure from the ultrasonic or any signal conditioning, wiring cost, or cost due to icing, that would be eliminated within the total accumulation of the total cost of owning an ultrasonic sensor. Now, we did also an analysis on identifying what the cost would be if we owned a mechanical heated anemometer, and the cost for this is actually higher compared to an ultrasonic sensor, where the cost of an anemometer that's heated is about $900. And when we looked into each individual item, it came out to $2,419 compared to the ultrasonic that's only $2,112. Now, if we looked at the cost in removing the cost of icing or removing the cost of additional wiring as well as signal conditioning, you could see that the cost of the mechanical heated anemometer dropped significantly to $1,147. However, the return on investment over the lifespan of the sensor could be within 3 years, as you can see here illustrated in the graph. After a certain amount of time, the accumulation of failures just keeps on increasing the cost of ownership of a mechanical heated anemometer. This graph shows if we were to incorporate the cost of icing in the mechanical heated anemometer. The reason for this is because we've heard within the market space that even though they're owning heated anemometers, there tends to be icing formation and causing of failure points within these sensors. So if we took into account the cost of heating or the cost of icing due to production loss, the cost actually comes out to the same as if you didn't have a heated, or if you didn't have if both the heated and the mechanical non-heated were incorporated. So the cost comes out to $1,819. So again, the return on investment could be simply within a year of purchases compared to the ultrasonic anemometer. What we really wanted to highlight in this slide is that if you take into account icing is a really big cost adder in regards to the ownership of mechanical sensors. As you can see here in the first section or the first column, this is a column illustrating mechanical sensors that are non-heated. And the total cost within a 5-year timeline of owning a non-heated mechanical anemometer is 53% of the cost due to icing. For the second column, we didn't illustrate icing because we said, well, if the mechanical sensor is heated, then you won't have that additional cost. But as you could tell, because of the failure points that tend to occur, it's definitely more expensive or double the cost compared to an ultrasonic. And of course, with the mechanical with communication protocol, you would remove the cost of signal conditioning or additional wiring, but there's still the cost of about 48% due to icing that occurs. Again, these other additional costs are not incorporated within the ultrasonic because there are no signal conditioning or icing issues that could occur. When we did the analysis over a 20-year timeline, it really highlights and illustrates why using an ultrasonic sensor would be the most ideal way to reduce costs and increase production. In this table, it shows the 5-year cost of the anemometer at using at a 100 turbine wind farm installation, where we're kind of estimating that that's about the size of a wind turbine farm. At 5 years, the cost of owning an anemometer is $211,230, which equates to the cost of a single anemometer times 100 turbines. And then when we did this correlation across all the other ones, you could tell that the lifespan of owning a heated mechanical anemometer or a non-heated mechanical anemometer is double or almost twice the cost of owning ultrasonic. So we recommend going with an ultrasonic anemometer just because of the cost savings that you could incur by going with one of our sensors. So don't take our word for it primarily. We've worked with other O&Ms. Currently, like I mentioned on the call, we also have a representative from AES. AES has incorporated our product offering for their wind turbines and replacing a lot of the mechanical anemometers to our Ventus platform. Terragen is another O&M company that we've worked with that is also doing the same. And then we also have OEMs like WEG and Goldwind who are using our Ventus and have standardized on our product offering because they also see the benefits of using our technology. Now, what we're asking for you is to look at your current wind farm and identify where our potential technology would be most ideal for your installations. We understand that there's about 48,000 installations out there, and we feel that there's a need for our technology to be incorporated within the American Wind Energy department or industry. I did want to give you a heads up that I will be at the AWEA show on May 25th from 4:30 to 6 p.m. during the poster session, where we're going to be having a poster describing and talking about just this analysis and the data points that we did to get the data points that we have and presented to you today. In summary, let's help you save in operational costs and increase production. Like I mentioned today, you could have a return on investment on your sensor within 1 to 3 years. And I've provided my contact information should you have any questions or any concerns in regards to the numbers that I presented to you today. Paul?
My phone.
I agree here with Paul. You there?
Okay, there I can. I can't hear you.
There you are.
Can you hear me?
Now we can hear you, Paul. Yes, we can. Looks like we're having some technical difficulties with Paul. If at this time, I think we have some questions, so I'll help Paul out here a little to see if we could address some of these questions. So one of the questions I have here was, what's your assumption that mechanical sensors are replaced annually? From our history and from talking to a lot of the owner-operators, we were told that replacements are occurring about 40% of the time. So there needs to be a replacement at least in 40% of the time when they are installing the mechanical anemometers. Another thing is that they're replacing them because they need to be recalibrated on a yearly basis. Tristan, are you there?
Yes.
So,
yeah, I'll
to answer yeah, go ahead and chime in.
I'll elaborate a little bit on that. So what we found with the mechanical sensors are over time, as the bearings gain rolling resistance, they tend to be reluctant to spin as fast as they should for a specific wind speed. So what that actually does is it creates a condition where that the cups aren't able to accelerate or decelerate at the same rate as a calibrated sensor. And at that point, the turbine controller is no longer able to calculate a correct turbulence intensity, which is extremely critical in terms of how fast the turbine needs to spin its rotor and how much energy is actually being felt actually through the drivetrain, main bearing and namely the planet stage. So a lot of people won't notice this because it actually starts making the turbine look more efficient because it's actually underinflating the perceived wind speed. So the basis of changing them yearly is so that the turbines aren't operating in that type of condition, which is extremely fatiguing on the drivetrain. But if you go by like the ICE-free 3 anemometers from NRG, they recommend every 2 years minimum replacement. The KK sensors, it's every few years. So it depends on the type of sensor and also the operating environment. If you have a lot of thunderstorms or extremely aggressive wind shear, they're more susceptible to acceleration during shear conditions or turbulence. So if that helps.
I appreciate that. Paul, are you able to get it back on? Can you hear us? I think we lost Paul. Any other questions from the market or from the webinar? Sorry.
Hey, Abraham, this is Stacy. I think we lost Paul. His phone doesn't sound like it's working at the moment. We do have another question that came in. It says, can you comment on signal noise with the Lufft Ultrasonics?
Great. Well, I think, Tristan, that you've worked with the ultrasonics primarily. Do you have any insight from directly working with our sensors in regards to signal noise?
So far, we have not seen this, but we have had some of the GE retrofit ultrasonics that use the FT sensors that initially overestimated wind speed by 40 to 50%. It was huge. But what we've found is because the ultrasonics are more responsive, there's no rotating mass, so there's no inertia. So they're instant response time, whereas mechanical sensors have what they call a recovery distance. So it takes several meters of winds passing across that sensor before it can accurately provide the true wind speed. So what you would typically see on a transition from mechanical to ultrasonic is you're going to change the slope and offset that is programmed either in the controller, or if you don't have access to that, you change it in your signal conditioner. In terms of noise, we haven't seen that, but it is very critical to maintain your shielding that runs along the cable from the ultrasonic. As long as it's shielded and grounded well, there's no noise interference. And typically we like to pull Modbus, which is also not susceptible to noise. Now analog, I believe they use a balanced output so that anything's induced on the high side signal is going to be equally induced on the low side signal, and the delta between is going to be the same. So I have not, with the Lust, experienced that scenario.
Okay. Did you answer Jim Salmon's question? Okay. All right.
Hi, Paul. Welcome back. No, we have not asked Jim's question, so if you want to go ahead and ask that one.
Okay, very good. All right, here's a good one. What is the realistic cost for replacing an existing anemometer with a sonic anemometer include? That includes wiring, for example, consider wiring, reprogramming of the SCADA system, modification of mechanical mounting systems, and are there others? And what are other costs? Maybe, Tristan, maybe you could answer that one.
Sure. So, of course, when you buy the sensor, you're going to have the cabling. And depending on the turbine type, it's real simple to go down to a local machine shop and have them just make you basically an adapter. So whatever the prior sensor, whatever methods or means they use to attach that to the met mast, you would basically just make an adapter that allows for you to install the ultrasonic. And so that's probably what we've seen, about $50 a piece. It's not a real huge commitment. Also, depending on the turbine type, you'll either have to borrow power from an existing power supply in the turbine if it has enough headroom, or install, like I said, a relatively fairly cheap power supply on the cost of about $200 to be independently providing power to that sensor. Other costs, our technicians have gotten the transition on the GEs and the Siemens down to about 3 hours, so they do two a day, fairly easy. And like I said, the wiring that comes with it is more than enough to reach most of the turbine nacelle control systems. So there's no additional wire to be added, and most of the sensors actually have pretty good size gauge, especially the heated sensors. So you a lot of times can use the existing wires and not have to reroute. It really cuts down on time.
Okay, very good. Hey, Matt asked a good question here. He says, are the sensors subject to foreign objects being struck in the sensor cavity does that obstruct readings then?
I can answer that.
Maybe Abraham?
So from our history, we actually, and that's a great question, by the way, because when we look at our competition has open prongs where birds tend to come in and poke at those sensor heads. The way our design is structured is that the two plates don't prevent or actually don't allow birds to really go in. They don't really like to go into that section. We haven't seen any concerns or any issues with spiders or objects going in. When we do see obstructions occur, it's primarily maybe a piece of paper that might have flown in there, but you could see the air quality drop, but it just stays there for a little bit and goes away, primarily because of the way the channel works or the tunnel works, kind of causing the air to kind of flow throughout the entire area. So as far as objects or insects trying to get there and nesting, we really haven't seen any of that occur within our sensors. I don't know, Tristan, from your history, have you seen any of that?
No, we haven't seen any problems. Especially they actually passed the military standard for ice prevention. So that was one of our bigger concerns. One thing I'll add on icing is the mechanical sensors, even the heated ones. What will happen is they'll start accumulating a layer of ice on the cups, which not only adds to their weight, but it impacts their efficiency in capturing that air moving past them. So what will happen is it would underreport the wind speed to the point that the rotor, especially on variable speed turbines like Siemens, GE, anything that has a converter on rotor or full converter system, they try to maintain a certain tip speed ratio to the oncoming wind speed. So what will happen is the turbine thinks there's low winds and will under-rotate the rotor. At that point, the airfoil does not work as it's designed, and air is allowed to go around the leading edge, and at that point you reduce your radial thrust and increase your axial thrust, which is, of course, if there is icing, the grease isn't going to be very warm in the bearings, and you really don't need that axial fatigue at that point. We've got strong evidence that we've lost several main bearings and planetary stages because of operating in this condition, but the turbine's unaware of this. So yeah, I wanted to add that.
Okay, very good. Jim asked the question, how is the sensor aligned for direction? Maybe Abraham, you can answer that.
Yeah, all our sensors have a arrow on the top of the sensor and on the body of the sensor that points north. So all you'd have to do is get a compass to either point it to north. In this particular case, for wind turbines, you want to point it to the nozzle. We do have an offset of 180 degrees that could be done through the software, and you could do an offset of 180 degrees as well. It depends on the installation. I've seen installations where they put the arrow directly to the nozzle. I've seen installations where they put the arrow pointing the opposite way with an offset. So that's kind of the way the alignment's set up.
Okay, very good. All right, Matt asked a question here. He says, it's my understanding that the Bachmann control software cannot currently take advantage of more precise wind direction measurements, which actually leads to an increased yawing. Well, I suppose it's not really a question. Is that your understanding too, Tristan or Abraham?
Actually, with the SLEGEs that we've employed these sensors on, which will actually be 155 of our units by the end of the year, we've actually seen better yaw tracking, and I think it's more to do with the mechanical sensors. You're not able to correct for the nonlinear cross flow that the rotor creates depending on its rotor RPM. So we've increased yaw tracking. For instance, one of the criteria we use is how often is the turbine plus or minus 10 degrees from true wind direction. And how we verify that is we mounted a nacelle LiDAR, and that way we know the true wind direction. And we've went from probably 70 to 75% maintaining between the plus or minus 10 degrees to over 98%. So it's all about, it's not necessarily a single correction, a single yaw bias correction. It's nonlinear. And we've actually increased the yaw tracking significantly, and there's room to improve that because maybe you don't want it to yaw as much. Maybe you have some yaw drive or yaw engine problems, and you want to reduce that. It's all, you can do it on the fly. So it's basically what works best for your environment. Another big plus is with infinite degree range from 0 to 359.9 degrees with the ultrasonic, you're able to do a weight management control algorithm. So if you have huge parts that have multiple rows and there's a lot of supplemental weight that reaches these further down the road turbines, you can use that sensor to say, okay, I want to offset these few turbines a few degrees so that we can shape the wake and actually impact how the wake influences the turbine downstream. So there's so much potential we're barely tapping into by using this type of sensor, and basically the only limit is the programmer to condition the signals. So we're real excited. This is going to be a long-term project for us. But so far we've seen, just from doing a static 2-degree yaw bias change, we've seen just over 2% increase in AEP. And we've also seen a lot less drivetrain component failures because there's no mechanical parts to degrade to alter that wind speed perception.
Well, that's good news. That's remarkable too, by the way.
Yeah,
2% increase in AEP for a 2% correction. Yeah. Is that linear? I mean, did you get 3% out of a 3 or 4% out of a 3 or 4% yaw error?
Of course, it's going to be dependent on the distribution of winds you see at a certain site, the air density, turbulence, those kind of things. But I would say most of our projects are right in the heart of the wind capital. So there's a lot of farms around here that could really benefit from it, and we're working on some that are on mountaintops with a lot of shear. So we're going to be able to use this to correct for the shear to reduce drivetrain loading and probably increase efficiency there too.
Okay, that's terrific. All right, Jim asked another question here. He asks, he said, maybe I missed this, but what was the recommended maintenance interval for the Ventus anemometer, and what's its cost? I think you mentioned cost. Abraham, that's one for you.
No problem. I could definitely answer that. And I'll piggyback on Tristan on the maintenance interval, but as far as the manufacturer comes into play, with the mean time between failure of 22 years, for this analysis, like I mentioned before, we did the analysis of 5 years, assuming that's safe. The Ventus anemometer said, hey, no more after 5 years. That's what the analysis came out to be. So as far as where we are in regards to cost, the base price for the sensor is $1,145. That's what we're marking it out to wind turbine manufacturers or wind turbine operations and maintenance. So that would be the cost just for the Ventus anemometer. As far as the maintenance interval, Tristan, do you guys have a preventive maintenance that you have to do? We don't have to. We actually, as a manufacturer, don't really have a maintenance interval because it's a really robust sensor. But I don't know if you guys have established something like that within your organization.
No, actually, the turbines we've retrofitted, we haven't had to go back to them. So in terms of maintenance interval, typically with mechanical sensors, you would start seeing problems in the perceived turbulence or, compared to Met towers or neighboring towers, wind speed deviation, stuff like that. But so far, I think the limiting factor is how you choose to convert the signal. So the sensor is definitely not the Achilles heel in this type of retrofit. So if you find a durable PLC, or I think y'all are working with a programming company that has developed the WindBridge, I believe, that has a multitude of outputs depending on the turbine. So in terms of maintenance, we're expecting every 15 years to have to service the system. Okay,
that's a good period. Jim asks again, are the units plug interchangeable? Maybe Jim, you can qualify that. I think you're referring to the mechanical, to the ultrasonic. Or is it necessary to reprogram calibration coefficients when a unit is replaced? Abraham, you want to try that?
Actually, I think more to Tristan. When you did the replacement, did you have to do any calibration coefficients replacement, Tristan?
No. The Lufft sensors come pre-calibrated, and since they're digital, there is no degradation of perception. So unless maybe there's some damage to the sensor, something happened, struck by lightning, there's no need to recalibrate. So it would be, once you have retrofitted a turbine with the ultrasonic, it would be plug and play if you were to have to change it. So we haven't had any failures yet, except for one that has been dropped from the turbine, and I wouldn't expect any sensor to survive that.
Okay. All right. Thank you. All right. Maybe, ladies and gentlemen, if you have any other questions, please type them in. Here's one for you, Abraham. What do you need to know to integrate the Ventus into legacy turbines?
Well, primarily we want to understand what type of anemometer is currently being used. We want to understand what model number, if possible. If you guys have the schematics of what the type of inputs that the turbine is actually providing, that will allow us to then try to mimic that same type of input to the current turbine controller. And we understand that every turbine is a little different. We understand that the schematics might be a little different, but we can work with you in identifying what would be the requirement to be able to replace the current mechanical devices or the current anemometers to the Ventus.
Okay. All right. Then I'll ask one more question. I think maybe you mentioned this early in the presentation, Abraham, but what's the mean time between failures for the Ventus sensor?
Right. So what I mentioned in the presentation was that at 20 degrees Celsius, our calculations came out to 22 years for the Ventus to operate. So that's the mean time between failure for the Ventus wind sensor. So okay. Overall, of course, it will vary depending on the installation and where it's at, but on average, 22 years.
Okay, so you should just about outlive the turbine, huh? Okay, any other questions, ladies and gentlemen? Your last chance. Okay, well, we're out of questions, so once again, the webcast will be available for reviewing at windpowerengineering.com and the URL that we used today. One final message, you can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. So this concludes our program. I want to thank Abraham for the fine presentation and Tristan for the assist in questions and answers, and everyone else for their good questions and their attention. So from the staff here at Wind Power Engineering and Development and from Lufft USA and Tristan's AES, we wish you a good and productive afternoon.